Hey everyone, so today we're gonna finish up most of our carbonyl chemistry by talking about carbonyl condensation reactions. And the first reaction we're gonna talk about is the Aldol reaction, but what is a condensation reaction? Well, condensation reaction implies that we take small molecules and we combine them into a larger molecule. Right? That's just like condensation takes of water takes molecules that are far apart and brings them together to form liquid phase. It's the same idea here with molecules. And so carbonyl condensation reactions do this while focusing on chemistry around carbonyl or ketone, ketones, aldehydes, carboxylic acids, derivatives of carboxylic acids, functional groups. Right, so we're going to use condensation. That's different than what we've used in the past when we talk about alkylation and whatnot. And generally, the idea with a condensation reaction is one carbonyl forms an enolate ion. We'll talk about that in a second. The other one acts as an electrophile to form carbon-carbon bonds. And so we're going to take this enolate ion, and the enolate ion is going to look something like this, right? This is our enolate ion, and this is going to attack another carbonyl compound, very electrophilic or partially positive carbon. And when we do that, that's going to allow us to form carbon-carbon bonds. So the first reaction we're going to talk about is a Aldol reaction. And so this follows a general reaction to form an electrophilic, basically an electrophilic carbonyl-carbon, and the type of compounds that these form are called beta hydroxy carbonyls. So if we have a carbonyl compound here, this is the alpha carbon, this is the beta, there's going to be an OH group on the beta carbonyl compound. And these are also known as aldols, and that's because they're usually the combination of an alcohol and an aldehyde. And so the exact position on the equilibrium of these reaction conditions depends on the reaction conditions and the reactant structure, right? So when we have these types of reactions, so if we had an aldehyde plus, or just let's say we had two aldehydes, and we put them in, conditions that form a condensation reaction, which would be something like this maybe, then this equilibrium can either shift towards the condensation products or the reactants, right? So we might get something that looks like R, something like that. So we might get something like this, which is our condensation product, but this equilibrium shifts back and forth depending on the reaction conditions. And so generally, the rule of thumb for these, reaction favors condensation in aldehydes with no alpha substituents and favors the reactants in cases where we have disubstituted aldehydes and ketones. And so this is most likely due to steric hindrance, right? If we have a ketone instead of an aldehyde, it's going to be easier, or sorry, not easier, it's going to be harder to attack the carbonyl carbon from the enolate ion, or with the enolate ion, which we'll talk more about what that actually means in a second. So if, an example of this would be if we had phenyl acetaldehyde and we had two equivalents of this, and we put it in conditions to start condensation, then this would be 90% most likely favoring the formation of the products. Right? But if we had something where we had two equivalents of cyclohexanone, for example, and did the exact same thing, then the reactants are going to be favored in both of these reactions. All right, and we'll talk specifically how do we get these different structures that I'm looking at here. All right, so based off of the general rule of thumb, which is that aldehydes with no alpha substituents favor the condensation, and then then reactants are favored in the case of disubstituted aldehydes and ketones. Okay, so what is the general Aldol mechanism? Well, I told you that usually this is going to be base catalyzed, not base catalyzed, but base promoted. Base promoted. All right, and this is an important distinction between being base catalyzed. And we're going to have our alpha carbon. All right, so if this is, why can't I erase? R prime. We're going to have our base come and abstract this hydrogen, and then this is going to create an enolate ion. And I'm not going to talk about the exact formation of the enolate ion, but the enolate, because we talked about in the previous chapter, but the enolate ion is going to look something like this, and it's going to have a minus charge on it, which is why it's called an ion. And then this is going to be attacked by another equivalent of this aldehyde or ketone that's not in its enolate form. Keep drawing it on accident. All right, so this is not going to be in its enolate form. And the electron-rich double bond can attack the carbonyl carbon on the non-ionized version of the enolate form while recreating the ketone functional group and then generating the O- on the unionized version of the aldehyde or ketone. And so this is going to combine formation of an enolate ion, which is important for alpha substitution reactions, and then also nucleophilic substitution, that carbonyl substitution that we saw earlier in these chapters as well. And so this is going to give a product that's going to look something like this. R prime, and then O minus. And we kind of get this interesting looking tetrahedral intermediate. And then the protonated version of the base can then come and take this hydrogen off the base, and we will get our final product, which has formed a new carbon-carbon bond, which is why this reaction is important. R, O. And then this is on the alpha carbon now of our original aldehyde or ketone, which is the one that got ionized. But then the hydroxy group is now on the beta carbon in our new molecule, our condensation product, right? So I drew this in terms of arbitrary reactants and products. Obviously, if you have an aldehyde or a ketone, one of these R groups is going to be a hydrogen or something along those mechanisms. So this is the general mechanism for the aldol reaction. And so it's a base promoted reaction, right? Because we have to consume an equivalent of base in this reaction. The product that we make is going to be a beta hydroxy because we have it on the beta carbon now, carbonyl compound, right? So we regenerate our carbonyl, and then on the beta carbon we have a hydroxy group. Okay, And so you might ask yourself, well, how do we know when we have carbonyl condensation versus just an alpha substitution reaction? Because both of these require the formation of an enolate ion and require basic conditions. And so generally, we need a full equivalent of base to generate an enolate ion, and then rapidly add an electrophile to quench the enolate ion. And so this would be for alpha carbon substitution, right? We don't regenerate the base because we need an equivalent of base to create the enolate ion, and then immediately it's quenched with whatever the electrophile is. Aldol condensation only needs a catalytic amount of base, and so this can be a weak base as well, to have a large amount of carbonyl compound to be present in the presence of the enolate ion, right? So the idea here is we promote the enolate ion, or we add just enough base to convert some of the carbonyl compound to the enolate ion, and then that enolate ion is very reactive, and it's going to be surrounded by a bunch of the unionized ketone or aldehyde, or even carboxylic acid, present in solution, and so it will react with those to form a condensation product, right? So this is going to be the conditions for a condensation product. And so we can remember this because for an aldol condensation, the base is regenerated, which is what we saw last slide, right? We end up with base here, again, at the end. The base is regenerated, so we only need a catalytic amount of base, whereas for a alpha alkyl substitution reaction, no base is regenerated because the enolate ion is quenched with an electrophile rather than allowed to react with another carbonyl compound. And so that's how you're going to determine whether or not you have an aldol condensation versus alpha substitution reaction. And so the end this lecture with is the dehydration of aldol products, and this is what you guys did in your aldol condensation lab. So I'll put up here aldol condensation lab. Is you basically you got rid of the hydroxy group on the beta, and then you replaced it with a double bond or an alkene, and then so you derived something that has a ketone or a carbonyl compound, and then a ketone group there. And so these are called enones. And so this can occur via acidic conditions or basic conditions. And so if this is driven after you've already generated your condensation product, so this is going to be your beta hydroxy R, and then I'm going to make this look a little nicer now compared to what we had last time. This is going to be R prime down here, and then you have the OH, and then if this is di-substituted right here. So we have something like this, and we'll have two different reactions for how this can proceed. So I'm going to duplicate this, put one down here. One's going to be acidic, and one's going to be in basic conditions. If we're doing it in basic conditions, what's going to happen is we have enolate ion that we generate is going to be negatively charged. And so the specific mechanism for how this happens is, the specific mechanism for how this happens is gone over in last week's lectures. So the enolate ion is generated, and we get the leaving of the base, and we get our enone product here. All right, so we lose a hydroxide ion, OH minus, and the version of the enolate ion that we make is charged. So this differs from when we have acidic conditions because we don't generate a charged enolate ion. Instead, we generate our R prime. We generate the enol, right, because it's a protonated version. So this is the enol. And when this happens, we get protonation of the oxygen here, or the hydroxy group, which makes it a good leaving group, so that when we get rearrangement of the structure, we regenerate our ketone. And when we regenerate our ketone, we end up with the same product. Which is our enone, right? So that's the enol generation versus the enolate ion, right? So that's, you get one of these two. You can go proceed with dehydration in both of these ways. And the idea is you generate an enolate ion again. You add acid or base, which will then protonate or deprotonate the hydroxy group on the enol, which would make it either an enolate ion or just the enol, which we have in the acidic conditions. And then you'll get expulsion of the either hydroxy from the acidic or basic conditions, or the H3O plus from the acidic conditions. And so the real benefit for doing this dehydration reaction is it can drive the total reaction towards the aldol product formation, right? So if you have your aldol reactants, you go through an aldol condensation step plus OET, you're going to have your beta hydroxy ketone. And if you lower the concentration of the beta hydroxy ketone by then going through either base or acid catalyzed to then make your enone, right? So if you force the reaction to move this way, you're lowering the concentration of your beta hydroxy ketone, which is going to push this reaction towards completion, right? So this is the same thing with Le Chatelier's principle. This is going to push the reaction towards completion, or towards the condensation products, because you're lowering the concentration of the condensation products by forcing another reaction to happen, which is the dehydration. So that's the real benefit to this, because you can always rehydrate that double bond if you need to, but this will push the equilibrium towards the formation of the beta hydroxy ketone. Whereas without it, if you have, something that only has, disubstituted aldehydes and ketones, it's going to be pretty hard, because naturally you're not going to want to form the condensation products. You're going to be happier staying in the reactants side of this equilibrium. Okay, so that'll be it for today's lecture on the dehydration of aldol products, the general mechanism for the aldol reaction, and also how do we know, if we get aldol condensation versus alpha substitution. So next time we're going to talk about a little bit of synthesis with aldol products, and then also mixed product aldol condensation, which is what you guys did in your lab, and then intermolecular or intramolecular aldol condensation.